All right, this is Precalculus Practice Test number 3. It is big. Let's jump in. In number 1, we're asked to graph an exponential, which is one of the precursors to graphing a logarithmic, but we don't do that until problem number 30, I believe, somewhere around there. To graph this, you can use a table if you want, or you can use a trick. I'm going to use a trick. I'm going to use a table. I'll use a table and then I'll use a trick for maybe the other ones. The general idea behind the table is you have an x, the input, a y, the output. The x, the input, should be much smaller than the y, and you're trying to choose some nice value for x. So usually a nice value is always something that will make this 0. So if I make it 0, then the output is going to be 2 times 1/2 to the power of 0. And anything to the power of 0, this is to the power of 0 is going to be 1. 2 times 1 is 2, so the output is here is going to be 2. What's another value to plug in? Some people might think, oh, -1, but some people might think 1. If I put in a 1 right here, watch what will happen. This will be a power of 1, and 1/2 to the power of 1 is 1/2. 2 times 1/2, I guess, is an okay value, but eventually I don't like fractions. I want to try to get rid of that fraction. So let me go the other direction. Let me go to -1 and show you what happens. When I go to -1, something really nice happens. I'm going to get 2 times 1/2 to the power of -1, and because I have a power of a negative, that means that inside here is going to flip. It's going to be the reciprocal. This is really going to be 2 times 2 over 1, again to the power of 1, which I can kind of ignore. And this is now going to be 2 times 2, which is just 4, which is a nice number. When you have negative powers, the fraction will flip, and you'll not have a fraction. That's why it's nice. So when I plug in -2 here, I'll get an 8. When I plug in -3 here, I'll get a 16, etc., etc. And you can kind of see the pattern already. It's times 2, times 2. Everything's times 2 to jump to each step, right? And that's because I'm going backwards. I'm doing the opposite of this 1/2 means divide by 2, which is why I'm multiplying by 2 over here. So you can make a table over here. It's the, what's the word I'm looking for? The brute force attack of, it will always work, but there's tricks. Let me now move into the trick. The trick for number 1 is you will always, as long as there's no weird thing happening up here, this is always going to be the y-intercept. So just graph the y-intercept of 2. Okay, you got a point. All right, and then as I move to the right, I'm multiplying by this number. As I move to the right, it's half of that. So I move 1 to the right, and then I had a height of 2, and now half of 2 is 1, so it's going to go down 1, but I want 1 right. So my new point is going to be here, which I'll do in pen, and I go right 1/2, right 1/2, right 1/2, and eventually I'm going to be on this line down here. You don't actually touch the line, but you get infinitely close to it. So when I draw a picture, it looks like I'm essentially going onto the x-axis. If I go to the right and I'm taking half, if I go backwards and I go to the left, that means I'm multiplying by 2, which is the pattern that we saw in our table. We're multiplying by 2. So over here, I'm going to take 2, and I multiply by 2, and I get a height of 4. Multiply that height by 2, and I go to 8. Multiply that height by 2, I go up here to 16. It's going to be right over here. And that's kind of off my table, or off my graph at that point. I can't graph 32, and I go ahead and do my best attempt to connect those with some sort of curvy exponential line. I'm trying my best. It's hard. It should be nice and smooth, not all jagged. And again, this line does eventually come down, and it looks on the line like I'm coming down to the x-axis. You don't actually touch it, but in our drawing, it does touch. Cool. And just remember, in terms of points, what I'm looking for, make sure you have at least 3 of these points correctly marked. You don't have to have all these, I guess, these fraction points. They don't need to be there, but at least 3 points is what I'm looking for, making sure that it does have this horizontal asymptote on the x-axis. That horizontal asymptote will be the same in number 2, but I'm thinking 3 and 4, the horizontal asymptote is going to move because we have this +2 shift and a +2 shift. How do we do number 2? I'm going to do the shortcutting method. Again, if you want to use a table, use a table. That gives you the general setup. But the general idea here is whenever I have this +2, this means take everything that you have and shift it left 2, which is weird because you normally think, isn't +2 to the right? Well, because it's up here and paired with the x, it's really the opposite. Whatever is paired with the x, you do the opposite in all of math, typically. So I'm going to pretend, okay, well, that would be the normal y-intercept, but I went left 2. So normally the y-intercept we said was at 3, right here, but we went right, did I just say left 2? Yes, we go left 2. So it's not here, we go 1, 2, and we have this point right here. That's the first point that you can go on your graph. And then normally when I go to the right, I multiply by whatever the base is. The base in our case is 2. So if I multiply by the base, going to the right, I multiply by 2. I have a height of 3. 3 times 2 is 6. So I'm going to come up to a height of 6. And I multiply by 2 again. 6 times 2 is going to be up here to 12. times 2 again, and we go off the graph because that'll be 24. And if I go to the right and multiply by the base, I can go left, and I'll write this note on here. When I go, I'm writing in like a weird color. If I go this direction, that's going to be divide. If I go this direction, that's going to be multiply. I'll just write multiply by whatever this base is. And that's always the case in these problems. There's a few tricks that you have to know along with those, but that's the general idea. So we multiplied, we went to the right. I'm going to divide by 2 to go to the left. So I'm going to the left, which means I'm going to divide by 2, or take half of it. So I have 3. Half of 3 is 1.5, and I can come down here to about 1.5. I want to go back to blue though. 1.5. Half of 1.5 is like 0.75. It doesn't really matter, but again, they're getting smaller and smaller. I'm just kind of eyeballing it, and eventually it's going to look like it's on the x-axis. Again, typically I don't look for these values. Most students won't graph the half pieces. And then you go ahead and connect them with a line. I'm going to choose red and just say, okay. They get connected with some, that's supposed to go through that point. Oh gosh. Yeah, I'm not the best at connecting these with a smooth line, but I'm not judging your artistic ability. Well, I might, but I'm not able to give you a grade for bad artistic ability, and I can't give you a better grade for nice artistic ability. I just care that you can find these points and know that there's some sort of 3D line that connects them. That's what I'm looking for. So again, if I was looking at this, I'd be like, those 3 definitely would be points that you should have, and that would be out of 4 points, and connecting them with a line. You don't even need to show any work for this one. Like, all of that stuff is done in your head, right? So I'm just checking those 3 points, probably 1 point apiece, and then making sure that you have a line with this horizontal asymptote at the x-axis. Now the horizontal asymptote down here is going to be a little bit different. This one is harder to do as a trick in your head, but I'll show you how to do it. You have to keep undoing and redoing this pesky trick of adding 2. If it helps to make a table, go for it. But the general idea here is you're going to, again, have this y-intercept of 5, except it's been shifted up 2. So I'm going to go to the y-intercept of 5. Up! It's gone up 2. It's actually gone up here to 7. So, and every time that I want to do the trick where I go to the right and multiply, you have to undo this vertical shift, which is kind of annoying. So I'm going to undo the vertical shift of 2, so I'm really at 5, and then I multiply by 2, which is 10. But again, don't forget to shift it back up by 2, and then I get a height of 12. So it's always unshifting by 2 and adding 2. So again, what if I unshift by 2? I come back down here to a height of 10. So once I have 10, I'm going to multiply by 2, and I get 20, and then shift back up 2, and I get 22, which is off the graph. But I mean, I can kind of eyeball it. It's right about there. What about going backwards? Every time you go backwards, it's kind of the same idea. We'll unshift by 2, come back down here. We were at a height of 5, and then instead of multiply by 2, we're going to divide by 2. 5 divided by 2 is about 2.5. Well, it is exactly 2.5, and then add 2 is going to be 4.5. So 4.5 is going to be right here. And I guess you need, I said 2 to 3 points, right? The 2 points that I would be looking for, make sure you have those 2 correct. Those are the really nice lattice points on your graph. This point, you don't necessarily need to have. The one thing that you really do need to have on this one is the asymptote has been shifted up 2. Notice that the asymptote in the last 2 problems was on the x-axis, on the x-axis. This one is actually off the x-axis. It's at 2. It's not on the x-axis. So I'm going to go ahead and draw that with a thick red line. I wish there's a way to do dotted lines on here aside from freehanding it, but I'm going to say that is my very thick horizontal asymptote. I'm going to do my best attempt of drawing a line that connects. Whoa, I need to not be a thick line right now. Thank you. All right. I'm going to connect this with a curvy line. Oh, goodness. And just kind of, I don't know, somewhere like down here-ish. And it will eventually, it looks like it's magnetizing to this line. Good enough for me. Arrow on that side. Arrow on that side. Do you need this point up here? No. Like, if you have an arrow right there, that's good enough for me. The really tricky bit right here is making sure you have that horizontal asymptote that got shifted up. Number 4 is going to be the same thing, but there's 2 different shifts. So if I were labeling this in English, I would have said this shift means go up 2, which does shift the horizontal asymptote. I had the shift up here, which was left 2, right? And then this one does 2 things at the same time. This says go right 1 and then go up 2. So there's 2 different things that are happening. You need to know what's really happening. So again, the original idea, the y-intercept is 4, but we need to go right 1 and up 2 from there. So here I go. The original y-intercept is 4. So I'm thinking right there, oh, but it has to go right 1. Oh, but it has to go up 2. Boink, boink. So it actually is up here. Okay. And again, this doesn't affect us anymore, or I guess this doesn't affect us anymore. I do know that I'm going to be multiplying by 2 to go to the right. This 4 doesn't affect us anymore, and I always need to undo and redo this shifting, which is kind of annoying. So I'm going to unshift by 2, boink, boink. That should go down to 4, yep. So it goes down to 4, and then I'm going to go to the right, which means I multiply by this number. So I multiply by 2, so 4 times 2 is 8, and then I reshift up 2, and I go up to 10. So my new height is 10. And then using that shortcut again, shift it back down, boink, boink, it's at 8. Multiply by this number, multiply by 2, 8 times 2 is 16. Shift it back up, 17, 18. So it goes up to a height of 18. And I think I can do the same thing in reverse. Let's test Mr. Sandell's mental math. So shift it back down to get ready to apply the factor. So shift it back down to 4. Now divide by this number. So divide by 2. 4 divided by 2 is 2. And shift it back up. 2 plus 2 is 4. So I have this height of 4. I think I can do it one more time and still have a nice number. So shift it back down. It was 2. Divide by 2. 2 divided by 2 is 1. And then shift it back. So I'm at 1. And then shift it back up 2. Boink, boink. And then I get this height of 3. And I know where the horizontal asymptote is because it's the same thing as last time. We shifted the asymptote up 2. We shifted this one up 2. So my horizontal asymptote, I'm going to make it a thick line as well. Maybe, can I make it a ball pen so it's more consistent? Instead of, these thick lines, I'll say it goes boink, 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 boink. That looks good. I shift the iPad around like a piece of paper. Let's come back to fountain pen, thin line, and connect this with, I don't know, like a black line. I don't want it to be a red line, so it's not confusing with the asymptote. And my black line is going to come down through these points. Oh, goodness. Make it curvy a little bit. Nice and smooth. And coming down here to that asymptote. It gets magnetized to that asymptote in the picture. I think that's correct. If it's incorrect, you guys can correct me and get extra credit, of course. All right, that was number 4. Let's move on to number 5. Okay, now we have to go backwards. We have to write an equation. Luckily, there's no shifting up, down, left. Well, sometimes there's shifting up. Look at that one. That one got shifted up. There's no shifting up in this one because the asymptote is still on the x-axis, luckily. So I'm just going to make it nice and easy. Do I need a function? I can just say y equals. So I'm going to say y equals. I'm going to do it a different color, though. Let's make it like a blue. This is going to be y equals. Okay, it's going to be the y-intercept. The y-intercept here is 2. And you're going to multiply by whatever you do to get from the right to the left. So let's go ahead and mark all the lattice points. I have a lattice point here, here. It's kind of hard to see, but I think it's at 18. If I had to say, like, this one looks a little bit to the left, that one looks a little bit to the right. So I think 18 looks like the right lattice point to me. So the question is, how do I get from a height of 18 down to a height of 6? How do I get from this point to this point? Or the easier question, how do I get from this point to this point? What do I multiply by? I don't multiply, Mr. Sandell. I divide. I divide by 3. That's fine. You can divide by 3, which is the same thing as multiplying by 1/3. Slap on a power of x, and we've got an equation. So again, the general idea here to find this point, if you ever forget, it's going to be the right height divided by the left height. So in our case, we had a height of 2 divided by a height of 6. 2 divided by 6 reduces to 1/3. There's no plus or minus a number over here because we didn't shift this horizontal asymptote. And you'll never, ever have a horizontal shift up here unless you're being super fancy, in which case, kudos to you. I'm not giving you extra credit, but I appreciate it. Just leave it X. It makes it nice and easy. You don't have to shift that over. All right, let's try this next one. So this one is hard because you have to unshift it. So let's go ahead and deal with the shift right now so we don't forget. It's going to be y equals some y-intercept times some thing that we will find using this formula of right height divided by left height. And then we are going to either add or subtract. In this case, we're going to add because we went up 2. I mean, the horizontal asymptote is at 2. So I'm going to be adding 2 to it right now. So I know I have a plus 2 because of this horizontal asymptote. What I need to do now is undo this plus 2 to the entire graph. Anytime that I have a lattice point, like so I have a lattice point right here. Anytime I have a lattice point, I need to unshift it. So let me mark all the lattice points so I can see them. I have a lattice point there, there, and I only have 2 lattice points on this entire graph. Well, you don't have very much of a selection. I'm going to unshift those lattice points by undoing this plus 2. Undoing plus 2, I was going minus 2, minus 2. So those are the blue points that I really want to be thinking about in order to find this number and this number. So notice that the y-intercept here was 5. So this number has to be a 5. And notice that this number, I went from a height of 5 to a height of 10, which means I multiplied by 2. Or you can use this formula. The right height was 10. The left height was 5. 10 divided by 5 is 2. So this number in here has to be 2. And don't forget this has to be to a power of x. So there's our equation. I'm not going to box it because there's not a bunch of work floating around where it's hard for me to see the answer. I will undo this underlining of 5, though. Excellent. And if you want a way to just check your work, plug in a number and see if it comes out. Like if I plug in 0, I should come up here to a height of 7. Should we check it? 0. 2 to the power of 0 is 1. 1 times 5 is 5. 5 plus 2 is 7. So it seems to be working. All right. Number 7. And by the way, once the clock in the top left is 2:52 right now. Once that hits 3:14, I'm going to stop the recording wherever I'm at, or maybe just finish the problem that I'm working on. All right, in this problem, this is before we learn logarithms. This is where we just wrote everything with the same base. Notice that 25 can be 5 to the power of 2, and 125 can be 5 to the power of 3. They have the same base of 5. That's the generic way that we're going to solve all these problems. Like, all of these can be 9 to some power, or if you're going to go overboard, 3 to some power. Look over here. 8, 2, 16, that can all be 2 to some power, right? So you always have the same base in these problems. Here's how I'm going to do this problem. I have a negative x. I'm going to use up this negative power and flip the inside, take the reciprocal of the inside. So it's going to now be 25 over 1 to the power of not a negative anymore, but a positive x, still equal to 125. All I did was use up the negative power to flip the inside. You're allowed to do that. And I'm going to rewrite this as not 25, but 5 squared. 5 squared is the same thing as 25, and that's still to the power of x. You don't have to divide by 1 anymore. 125, I told you before, is 5 to the power of 3. And then from there, I can say 5 to the power of 2x is equal to 5 to the power of 3. Why? Because a power to a power means multiply. And here's the trick. If you have the bases the same, the exponents must also be the same. Well, those are the same. So these 2x and 3 need to be set equal to each other, giving me 2x is equal to 3. And then I solve by dividing both sides by 2, and x is equal to 3 halves. Or if you want a decimal, 1.5. So I'm going to go ahead and box both of those. You can use whichever one you want. I'm pretty sure the answer key will have a fraction. I hope so, because I like fractions. All right, let's do number 8. So I'm going to rewrite everything as a base of 2. Well, let's just jump right in. 1 over 16 is now 2 to the power of 4. And this is going to be times, well, that's already a 2, so I'm just leave that 2 to the negative 2n minus 3. And that's going to be equal to, 8 is the same thing as 2 to the power of 3. All right, almost the same as everything, but the problem over here is that's on the bottom. We need to make u on the top, so we need to make this 4 negative, and then it can float up on the top. So I have 2 to the negative 4 times 2 to the negative 2n minus 3. That's going to be equal to 2 to the power of 3. Almost okay. Remember, I don't want one exponential on the left, one on the right. So I need to combine these two. Remember that if you multiply the same base, we really add these exponents. So I can rewrite this with a 1, 2 on the left, 1, 2 on the right. So 2 to the power of 3. But the thing on the left, I'm going to add those powers together. I'm going to get negative 2n minus 7. I added the negative 4, negative 3. And just like before, if the bases are the same, the exponents must therefore be the same because we have an equal to sign. So I can now say, how much room do I have down here? I don't have like a number 10, so I can keep going down. I can now say that negative 2n minus 7 has to be equal to 3. And then from there, I can add 7 to both sides. I get negative 2n is equal to 10, and then divide both sides by negative 2, and n is equal to negative 5. Final answer, and box it. Let's try number 9. I'm going to do it the easy way. If I had a problem where I randomly changed this 9 into a 27, I would have no choice but to write everything with a base of 3, because 3 to the power of 3 is 27, 3 to the power of 4 is 81. The common base would be 3, but this one I can use a base of 9, because 9 to the power of 2 is 81, so I'm going to make it easy. I'm going to say that this is really 9 squared is the same thing as 81 times, okay, I want to flip this thing, and I need to make this power negative. It already is negative, so a negative times a negative is a positive. And check this out. I have a 9 over 1. I flipped it. It's now to the power of positive 3x. That's going to be equal to 9 to the power of 1. So far, so good. Again, I'm kind of ignoring you, and I now have a multiplication problem over here. When I multiply same bases, I add their powers. It's going to be 2 plus 3x over here on the left. I'm going to have 9 to the power of 2 plus 3x is equal to 9 to the power of 1. If the bases are the same, their exponents must also be the same, and 2 plus 3x must be equal to 1. And I can solve. I can subtract 2 on both sides. I get 3x is equal to negative 1, and then divide by 3, and x is equal to negative 1/3. Final answer and box it. All right, let's move on to the next problem. We're doing well on time. Rewriting them in exponential form. So again, the way that I'm thinking about this is the what power function. What power does 16 need to be raised to in order to get 256? And the answer is right there. The answer is 2, so 2 is going to come right here. This is always the way that I think about this. And you can just double check. 16 squared is 256, so that makes sense. Cool. Number 11, you're kind of going backwards, and you can use number 10 and 11 back and forth to help you go between the two different forms. They're opposites of each other. Logarithmic is the opposite of exponential form. So again, I'm thinking of the what power function, but I have to write log, unfortunately. Log, and I don't think we have, we do have a base. The base and the base are always same, so that's another way to remember this. 16 is the base of the logarithm, and 16 is the base of the exponential. So the base over here is x, so my base over here is x. So log base x. And now it's time to think of the question. So log is always what power does x need to be raised to in order to get the answer right here? Well, the answer is 21, so 21 comes down here. You get 21, and the only remaining thing is y. And it makes sense to go back. Like if I read this again, I say, what power does x need to be raised to in order to get to 21? Well, x needs to be raised to the power of y. X needs to be raised to the power of y to get 21. So if you're really a master of the what power function in terms of always thinking of a logarithm like that way, I think it makes it a little bit easier. Let's move on to number 12. Oh, I love these. Okay. And again, these are what power functions. So I'm going to write this in ink. I'm thinking, what power does 7 need to be raised to in order to get 49? I can even write it out in my notes. 7 to this box, fill the box. 7 what power is 49? Well, that box has to be 2. 7 to the power of 2 is equal to 49. Moving on to 13. Again, I'm thinking of this as the what power function. What power does 5 need to be raised to in order to get 125? Well, 5 to the power of 3 is 125, so 3 is our answer. And over here, again, I always think about this as the what power function. What power does 5 need to be raised to in order to get it flipped and squared to get to 25? Well, flipping it will make us negative. Anything to the negative power will flip us. And to get from 5 to 25, we square it. So the answer here is negative 2. Let's do number 15. We're taking the inverse of each of these, and as you remember, this is a very useful skill in order to graph them. So we're now scaffolding how to graph logarithm functions. So I'm essentially trying to isolate the logarithm as my first step. So this pesky multiplied by negative 6 has got to go. So I'm going to have y divided by that negative 6 on this side. And now I have just log base 4 of x on this side. Now that the logarithm has been isolated, I can undo the logarithm. I can exponentiate with the same base. This is a base of 4, so I'm going to exponentiate with a base of 4, and I'll rewrite everything again just so it looks nice in the notes. 4 and 4 are going to be my new bases, and this 4 is going to be to the power of log base 4 of x. And this is going to be 4 to the power of y over negative 6. It's called exponentiation. You always exponentiate with whatever that base is. Here is the reason why. Because you get cancellations. You, and you are gone, and I'm left with x. Over here, I have 4 to the power of y. Ooh, I always make this mistake. And I did catch it before checking the answers, considering I haven't checked any answers. I forgot to switch my x and my y. I should have done that at the very beginning. I apologize. This and this should have been switched on the very first step. So I need to switch those throughout the entire problem. So erase, 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 erase. And I'm switching my x and my y's. My bad. I should have caught that earlier. X and my y. I won't make the mistake in number 16 or 17 though. So this is going to be an x, and this is going to be, this down here is also an x. Ooh, I want to make it red though. That's an x over negative 6. And over here I have y, and I have a blue y, and I think all of those have been switched now. All right, cool. I think I have my final answer. The inverse is 4 to the power of x over -6. Very nice. What about number 16? Again, switch your x and the y's. So I get x is equal to 5 to the power of y plus 8. Again, I need to isolate my exponential or isolate my logarithm. The only thing that's in the way is this plus 8. So you need to undo plus 8, and you need to have an x minus 8 equal to 5 to the power of y. That's a 5 to the power of 5. 5 to the power of y, there we go. And now I need to save Rapunzel. Rapunzel is trapped up here in her tower. The only way to save Rapunzel is to take the logarithm. So when I do that, I'm going to take the log of both sides. I'll do that in a separate step. I'll say log of some base of x minus 8 is equal to log of that same base of 5 to the power of y. And I get to choose whatever base I want, and the base you should choose is the base of the exponential, because things will cancel out. It'll be nice. Choose a base of 5. Choose a base of 5, and check this out. Cancel, 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 and you get y is equal to, just rewrite this again, log base 5 of x minus 8. Very nice. Do I need to be boxing these? I think it's pretty clear that my answer is at the very bottom, but just in case, there, I'm boxing my work. And, oh, there we go. I'm on to number 17. Doing well in time. We got 11 minutes, or a little over 10 at least. Condense the following expression into a single logarithm. All right, well, as a reminder, we are allowed to bring u up here, so this is now log of z squared. And the same type of thing, this is going to be a little bit more of a process. This is the same thing as plus 1/3 of log of x. And this right-hand side can also be thought of as taking our 1/3 and bringing it up to the power. So it's to the power of 1/3. And that left side is not going to change. I'm going to have to rewrite it a bunch of times, aren't I? Log of z squared. And if you know your fractional powers, you'll remember that's the same thing as taking a root. Not the square root, because it's not a 2. It's the cube root. So this is going to be log of the cube root of x. This is going to be log of z squared. I told you I must write this down a few times. And finally, when you add on the outside, you multiply on the inside. And this is finally going to be log, just one log, which is what it wanted me to do, a single logarithm. So it's one log, and I multiply the inside. It's going to be z squared, and just squish it next to cube root of x. There we go. I should box my work, shouldn't I? There it is. Here's my box. Number 18, no, it's down beneath us, not to the right of us. Expand, you're doing the reverse. So now the 5 is going to come down. Instead of coming up, you're allowed to come down. And I now have 5 log base 9 of u to the power of 5 over v. Okay, if I have division happening on the inside, it's subtraction on the outside. And I have a bunch of these 5 logs. So I'm going to say this is now 5 log base 9 of a thing minus, because there's division, 5 log base 9 of the other thing. We did u to the power of 5 divided by v, so u to the power of 5 and then v. Order does matter here, because subtraction problems, they do matter. Same thing with division. Division, the order matters. And finally, this power of 5 can come down yet again, and I can say that this is really 25, and then rewrite everything else. 25 log base 9 of u minus 5 log base 9 of v. And as a general tip, if you ever have a power, then it's not fully expanded. You should always be able to write it out front. Same thing up here. If you ever have a number out front, always make it into a power, and hopefully one of them on the quiz, if I've done it correct, will turn out to be a radical, a 4th root or a 5th root or square root or something like that. All right. Number 19 and 20. Oh yeah, these are the fun ones where you have to figure out, like, how can you only use multiplication and division with these numbers to get this? You're not allowed to use any addition or subtraction. So how do we get multiplication using 9 and 5? You're like, well, I see 9. How do I get a 5? There's no 5. And that's the secret 5. Remember the 2 secrets here. There's 2 things that are always nice to know, and I'll write them over here to the side. And here's the secrets. Log base 5 of 1. How do you, like, what power does 5 need to be raised to in order to get 1? Well, 5 to the 0th power is 1. And the other one that is always nice to know is that log, that was a terrible G, log base 5 of 5. And again, think of this as a what power function. What power does 5 need to be raised to get 5? Well, you don't change anything to it. You raise it to the power of 1. These are always the two special things that you can add on these types of problems. And you'll notice, hey, one of those is useful because these are the numbers that we're using. These are the numbers that we're using, right? Well, one of them is a 5, and we divide by that 5. So that would be nice. So here's what's really happening. This is really log base 5 of 9 minus, why? Because of division. Or again, if the inside is being divided, the outsides are being subtracted. Minus log base 5 of 5. There we go. I was like, what number do we have down here? It was a 5. 9 and 5, because 9 and 5, right? And then we can convert them with their names. What was the name of this one? Well, check it out. That and that are the same thing. So this one is named Y. What's a person's name that starts with Y? I don't know, Yvette? Yeah, I'm going to say Yvette because it's Miss Garcia, right? So this is going to be Y and then a minus. Log base 5 of 5, we name that one 1. Very creative. Y minus 1. So there's the answer. Y minus 1. Oh, Yesenia. Why did I not? I was like, there's a student that starts with a Y. It's Yesenia minus 1. There we go. Number 20. Again, let me write the hidden messages. There's a log base 5 of 1. That's 0. And there's a log base 5 of 5. That's 1. Let's see if that helps us. Somehow, only using multiplication and division, I have these 5 numbers, and I need to get to 120. How could I get 120? Well, I'm seeing a 5 times a 4 is 20, and 20 times 6 is 120. Do you guys see that? Yeah, so check it out. I'm going to do, this is the same thing as, here, let me move you guys up so I have some room. This is the same thing as log base 5 of 6 times 4 times 5. You can check that 6 times 4 times 5 is indeed 120. If I have multiplication on the inside, I have addition on the outside. So this is going to be equal to log base 5 of 6 plus log base 5 of 4 plus log base 5 of 5. And then you just have to name each of these things. What do we got? A 6, that's Sam, masculine or feminine. And we got a 4, which is Tom or Tammy. And then we got a 5, which is 1. Very creative. So what do we got? We said Sam plus T plus 1. All right. There we go. And we're getting low on time. Let me take a peek at the next one and see if I could even do it in time. No, yes, these require calculators, and I don't want to get that set up. So that'll be the next video, starting on number 21. Thanks for watching.